Hi guys, it's a guy Olunde. Today we'll be solving another one of the most commonly asked tech interview question. They build a binary tree from preorder and inorder traversals. It's a standard DSA problem that is commonly asked by top tech companies including Google, Amazon, Netflix, Microsoft, Apple, Meta, and other top tech companies. The problem statement states that construct a binary tree using arrays of value obtained after a preorder traversal and an inorder traversal. We are given this example input array for the preorder traversal and inorder traversal. So these are actually two of the three types of traversal that we have. So fine, we have the depth first search method and the breadth first search method, right? But preorder is just and preorder and inorder are two of the three type of depth first search method. So whereby preorder just means that we consider the so it simply means that we are going to consider we are going to process the current node, then we are going to transverse recursively to the left node and then the right node. That's what the preorder traversal does. While the inorder traversal is going to first of all process the left node before coming back to process the current node before going for the left and for the right node. So those are two type of traversal. We're going to be seeing it more into them in this video. So we are giving this input, we are giving these two inputs, and it yield this binary tree now. And then we are giving the constraints that the tree consists of unique values. The first question that might come to our mind is that why do we need both preorder and inorder array in order to solve this problem? The reason we need two traversal array and not just one is because one is quite insufficient. By giving us only one traversal array, just like the inorder array now, there are multiple tree that we can derive from this single traversal array, this inorder array. So one is this, which is the one that was given to us originally. Another one is this particular tree structure, and another one is this particular tree structure. Because all this is just trying to say is that for the inorder now, it can give us multiple possible tree, such that so far it satisfies the condition of that I state here, that it processes the left node first, then the current node, then the right node. So if you look at for example here, you see that by processing the left node recursively, it's going to first of all process node 2, right? Then it will come back to process node 9, which are the left node. Then to come back to process the current node. Then to now start to process the right node, and at the right node still is going to start from the left node. So meaning that even at the right node it's going to be 4 first, then 3, then 7, and that's why we have this array right here. So, and similarly, if you look at this structure too, it's going to process the left node first, then the current node, then the right node. So if you see that the left node here is 0, is null. It's actually null because there's no left node to this root node. So that's why we end up processing the right and the current node, which is 2, and before processing the right node by starting from the last left node the same way. It will go recursively down until you get to this last leaf node, the left node, and it's gonna bubble up again and do the same like that. So you will see that this same array actually is what we are gonna arrive at if we traverse this particular tree in an inorder method. I mean in an inorder format. So, and we even by passing and traversing this particular tree also in another method, we are still going to arrive at this same array, and this third one likewise will bring us back to this same array, meaning that there's ambiguity in using a single array. So therefore that's why we have to use both the preorder array and the inorder array, so we can arrive, so that at any point in time everyone is gonna arrive at a single tree, as a single tree structure. Don't forget that what we are trying to do is to construct a binary tree, you understand, just by using the preorder and inorder arrays. Now, whatever method and whatever way we are gonna be constructing the tree, one key feature that we need is the root node. So we first of all need to identify what is our root node, so that out of this root node now we can then decide to find the left subtree and right subtree. But the number one thing we want to, that is so important in a tree, is the root node. Now, to identify which of this node and which of these values is the root node, so don't forget that in each of the array, the value are unique from the constraint that is given to us here. So you see that in this preorder array, the value are unique. So this inorder array will also contain the same set of value as the preorder array, but in different sorting. So the sorting are different, right? Okay. To identify the root node, let's remind ourselves of how nodes are processed in each of these traversal algorithm. Don't forget that preorder traversal is just sort a kind or a type of the DFS traversal algorithm, while the inorder traversal is also another kind of the DFS traversal algorithm. So the preorder traversal actually processes the current node. So don't forget, traversal is all about moving from one node to another across the binary tree. So moving from one node to another until we get to all the tree in the node in the binary tree. And what preorder traversal does is that first of all it processes the current node. I mean the current node that it is. So after processing it, then we move to the left node to process the left subtree, right? And then it will then process the right subtree after having processed the left subtree. So, and this is just the code implementation, or a pseudo code is going to process the current node, and then it will navigate by recursively calling on the left subtree, and then it will now recursively call on the right subtree. And if we do like that, it's going to give us this array. So this array is actually an array that's a representation of how it's going to be printed. Let's say that how the value are going to be processed. Let's say that suppose in the process of processing the current node, what it's doing is that it's appending it into an array. So it's going to append 5 first, so and then 9 and then 2, where all of this value represents node values, right? So but for the inorder traversal now, it's going to process the left subtree, right, and then process the current node. So meaning that even if we are given a root node like this, what inorder is going to do is that it's going to go and target the left subtree. It's going to recursively call on the left subtree, and that's why you're not seeing 2 at the beginning here, and that's why you're not seeing 5 here. Why? Because it has to process this left subtree first, so which is, and the left subtree here is 2. So right, this is also a left subtree, right, but it's going to recursively call on the left until you get to a leaf node, whereby there's no more node to call on the left any longer, right? And that's why it process 2. So and that's what it does. So after treating the old left subtree, is now going to bubble up again and then now process the current node. That's why you see that the current node, which is actually let's say the root node, which is node 5, seems to be at the middle right here. Why? Because it's not going to process the root node at first. So unlike preorder that is going to process the current node, you can see that the preorder starts from 5, right? So because it's going to process current node, then process the left subtree, then process the right subtree. So those are the 3 differences between them. So the DFS, the inorder, those are the little difference between the preorder and the inorder traversal. You see that the inorder will process the left first before processing the current node, then going back to process the right node. Since in the preorder traversal the current node is processed before the left and the right node, we can conclude that the very first value in the preorder array corresponds to the root node. Just like we can see, you see that it's 5. So why? Because the preorder algorithm is going to process the current node, and since we are all going to start our root node, our processing from the root node, if you are to traverse this binary tree, for instance, now definitely we can be sure that if we are using preorder algorithm that is represented by this array, definitely it's going to process the current node first. It's going to process the root node first. So definitely the first element of this preorder array is the root node. So now we can see we've gotten our root node by just simply entering by selecting the very first element of this preorder array, because we are quite sure that preorder array is gonna target and process the current node before ever processing any of its left and right subtree. With this established, now let's find a method that we will use to construct the left and right subtree of this root node 5. Let us consider the preorder and inorder binary array. These two array, preorder and inorder array, and the corresponding binary tree that is formed by them. As mentioned earlier, we concluded that the first value of the preorder array, which is 5, actually forms is the value of the root node. So we can say we now have the root node 5. Now what do we do next to find the remaining subtree? The preorder array is actually not sufficient to get us all the remaining subtree, so we will do well to consider the inorder array. Now we have been able to use the preorder array to get the root node. Now let's consider the inorder array. The inorder traversal will first visit a node left tree before processing the node itself, just like I explained in this logic here. It processes the left, then process the current, then process the right. So, and because of that, we can conclude that every element to the left of 5 of this value 5. Don't forget that each of the value in this array are unique from the constraint that is given to us, and so we will be able to conclude that the very first element or very first value in our preorder array, which is actually 5, we'll be able to conclude that is our root node. Definitely we can say that every value to the left, which include 2 and 9 of the in the inorder array, actually are the left subtree of our node 5, which is our root node, and every element to the right of that value 5 in the inorder array corresponds to the right subtree. We can also visualize it here in the subtree. We can see that 5 is the root node, right, and 2 and 9 corresponds to the left subtree. So, and then 3, 4 and 7 corresponds to the right subtree. Now what? With the root placed, we have the root, right? We already identified the root. We have two things to build now: the left subtree and the right subtree. I mean the root left subtree and the root right subtree. Now come to think of it, if we build a tree starting from the root node and then we build the left subtree and then we build the right subtree, you will notice that we are effectively building the tree using the preorder traversal, whereby we start from the root node, then we build the left subtree, then we come back to build the right subtree. Now this is useful because we happen to have an array of we happen to have the preorder array, which means an array of value from the preorder traversal, and now we know the exact order in which the nodes are going to be created. What I'm trying to say is that since the nature at which we'll be creating this tree is actually corresponding to the preorder algorithm of building the current node, then navigating to the left to build the left node, and then the right node. So that order follows the preorder algorithm. And now that we happen to have an array of values that follows the preorder algorithm, so we can say that by building the tree that way, we just need to navigate through this preorder array one at a time. So meaning that we now know which node to create and which node to create next. So knowing that the first node is node 5, right, which is our root node, we can be quite assured now that the next node will be node 9 to create. Why? Because the way we are creating this array follow the preorder traversal of processing and building the root node, then building its left subtree and building the right subtree. Let's just look at it visually now. You see that if we follow that order, we can easily build our root node, which is node 5 right here, and then the next value in the array we build the node 9, which will happen to be at the left node. Don't forget that we decide to build the node and to build the tree in such a way that it will follow the preorder, whereby we have the left node and everything we want to build first is the whereby we have the root node and everything we want to build first is the left subtree before the right subtree. So by following this array now, we can just easily build 9 and then build 2, which corresponds to the left subtree, and after that we can now build this 3, 4 and 7 that corresponds to the right subtree. You see, just by transversing this particular preorder array, just by transversing it one after the other from 5 to 9 to 2 to 3 to 4 to 7. So as we are building the tree using the preorder traversal, the next node to be created at any point will be the next value in the preorder array. So this means we can just iterate through the preorder array to place each new node. So building this way, we know that after creating the root node 5, the next node to be created is node 9. But how do we know whether this node 9 will be to the left side of node 5, which is our root node, or to its right side? This is where Inorder array comes in, as it will help us to determine the structure of the binary tree. Now let's consider building the left subtree. Now when we want to build the left subtree of the root node, for instance, because so far we already found the root node to be node 5, so we look at the part of the Inorder array that corresponds to the left subtree. So looking at this Inorder array now, we know that the root node is at the middle. We know the nature of Inorder array is to actually process all of the left subtree before coming back to the root node before processing the right subtree, right? So we look at the side, which is actually this range of 2,9. This is the side of the left subtree, right? Here is the side of the left subtree. So, and then we try to check if it is empty or not. Fine, because it is not empty, what we do is that because it's not empty, we proceed to build the left subtree starting with node 9. So we are still following the array here because we are building the preorder traversal. So we are still going to follow node 9 and build the next node, which is node 9. So that is if it is not empty. I mean, if this side, the left side of the Inorder array is not empty, so we'll proceed to build 9. But if it is empty, it means that there is no left subtree, right? So the current node left side will be none. We're just going to set it to null. So the same thing also apply to building the right subtree of the root node, which is node 5. To build the right subtree, we're gonna go check in our Inorder array if the right subtree exists. You understand? At least if it's not empty, if it contains at least a particular value. So that way now we just know that okay, we are gonna make our next value in the preorder index. We're gonna make it the right. We're gonna create the node and make it the right side of node 5, right? So that is if it is not empty. Now let's devise a standard algorithm for our strategy for our algorithm now of how we're gonna be solving this problem. First, we are gonna create a preorder index. So it's just like a pointer that will point to the value of the current subtree node value. So what I'm just trying to say is that this preorder index will correspond to the preorder array, meaning that it's going to be working with the preorder array, while the Inorder index is going to be working with the Inorder array. So this preorder index, first of all, is going to point to the first element in our preorder array because that corresponds to the root node, right? So while the Inorder index is going to point to the position of this particular value that the preorder index is pointing at in the Inorder index. What I mean by that is that fine, the preorder index is pointing at node 5, right? So now what's the position of node 5? What's the index of node 5 in the Inorder index? The index the position is actually 2. So that's what because the index of node 5 here is 2. So that's what the Inorder index will be pointing at. So, and why it's pointing at that is because don't forget that even though our preorder index actually tells us what node to create next, because we are going to be creating it using the preorder traversal, the Inorder index is going to tell us how the structure is going to be like that. Okay, this particular node that we created from the preorder index is it going to be to the left of the current node or to the right of the current node, and that's why we need this position. So by this position now we can identify that, okay, everything, these are just the two nodes that we need to create to the left, and once these two nodes get exhausted and become empty, then there's no need to create anything to the left again. We can create to the right. So, and also it tells us that these are the three nodes that we need to create to the right. So, and after we created three nodes to the right, so there's nothing again to create. So it serves as a range. So that's why we are using the index. So we know that 0 to let me see, 0 to right from the root node 0 to 1. Why? Because we'll be using another index minus 1, right? Why? Because we want to build the range of the left subtree to be 0 to 1, and the right subtree to be 3 to the end, right? Why? Because this 5 itself is the index 2, so we add 1 to it, so that has to build the right subtree, and we subtract 1 so as to build the left subtree. So this is simply what we are going to be doing. So at each recursive call, don't forget we are using DFS, the preorder traversal, so it deals with recursion, recursively calling the current node left and right subtree, so as to keep on building until we get to the end. And at each call, what we want to do is to create the current node using the value pointed at by the preorder index, just like I explained. We first of all create the node, the current node, and what we do is to increment the next thing to do is to increment the preorder index, so that it could point to the value of the next node to be created. Meaning that this preorder index now will now point to 9. So we know that, okay, 9 is the next one to be created. So, and then we need to make the third step is to make a recursive call to build the current node left and right subtree, right? What I'm trying to say here is that we're going to make recursive call to the current node so that we can build its left subtree and its right subtree before we navigate to the next node. So, and how we do that is to pass in this subarray in order. So this particular range, like I explained, 0 to index another index minus 1, meaning that the range 2 and 9 is what is going to correspond to the left subtree of the current node, and the range 4, 3, 7, which means another index plus 1 to the end, which is n minus 1 to the end of the array, is going to be used to build the right subtree now. So yes, meant to be right. Now, one inefficiency with the above approach is that you see that each time we want to make a recursive call to build the current node left and right subtree, we actually extract. This is actually how would I put it? We're trying to build a subset, like extract a range of value from the original Inorder array. So, and that can take on time, where n is the length of the Inorder array. So it's not very efficient. So to make it more efficient, we are going to be defining the range of the subarray instead of extracting the whole subarray. What I'm trying to say is that, you know, in calling the in trying to make a recursive call to the left node to create the left node, we are going to be passing in 2, 9, and for the right, we're going to be passing in 4, 3, and 7. So instead of having to extract this thing, which is going to take one time, we can just pass in 2 pointers. So rather, the first pointer will point at the left, and the second pointer is going to point at the right of the subset, instead of having to take the whole number into a new array and return it. So look, for instance, now when we are trying to call make a recursive call to the left node of the current node, which happen to be the root node now. So you know it's gonna be left comma, it's gonna be 0 comma index minus another index minus 1, right? This range. So instead of having to pass in a new array that contains 2 and 9, we just pass in left and right pointer. So the left pointer is going to be pointing at 0, or it's going to be pointing at the left, while the right pointer is going to be pointing at the right, which is actually another index minus 1. So and similarly, if we were to call the right one, instead of having to pass in a new array of 4, 3, and 7, we just pass in a left and updated left pointer of another index plus 1, which represents the right boundary, and a right pointer of 7, which represents the last element in the array. So that way now is more efficient. Now, another optimization that's quite important is concerning how we are going to be getting the index of the value in the Inorder array. Don't forget that we are going to be traversing through the Preorder array, and each index that we come across, each value, we are going to be creating it, right? So we are going to be creating it in the same order as it is in the Preorder array, but we need to go and to be able to determine this created node that we create using the Preorder index, is it going to be to the left of the current node or to the right of the current node? That is going to be determined by the Inorder array. So, and how we can determine is by getting the position, I mean the index of that particular value that we extracted from the that we got from the Preorder array. We can find its position in the Inorder array. So, and to do this now, instead of having to iterate through it every time we are trying to find a position, we can just use a map. So whereby we are gonna use a map that is gonna iterate through, is gonna get each of these value in the Inorder array as keys, and it's gonna get their position as values. So that way now we can use O1 time, I mean a constant time, to get the position of each of these values. For now, like now in the map, I mean in the hash map, the value 5 will have a the key 5 will have a value of 2, which corresponds to its index, and that way you can easily navigate that. Okay, 0 to 2 minus 1 is the left subtree, and then 3 to n minus 1 is the right subtree, something like that. So that's the little optimization we'll be making there to make it more efficient. So we're going to be going to the code implementation now for a more better and rigid understanding of what we have been talking about. Alright, let's move into the code implementation for the for building a binary tree from Preorder and Inorder traversals. So we have our tree node class that we'll be using to create these nodes, right? And it has a value, so a value attribute to set the value. It also have a left and right attribute that is set to none by default. So similarly, we have this particular array, the Preorder and Inorder array. I got this value from the problem statement, so to represent our sample array. So, and now we'll be passing it to the Preorder and Inorder binary tree function. So let's define that function now. So it's the function that is going to be helping us to create the binary tree from the Preorder and Inorder array. So these are actually list of integers. They are simply integers, but we'll be creating a binary tree out of them, and as well the Inorder, which is actually a list of integers as well. So, and the return of this function should be let's just leave it as a node. It's gonna be a tree node because we'll be creating a node, right? Fine. Okay, sorry, I think here is supposed to be this. So alright, now okay, so what we want to do is that we are gonna be creating, because we'll be using like two functions to solve this problem, so it's not complex, but we just want to make it more simplified, right? And one is the Inorder index map, so which is going to be a map. Let me remove the global here, so it will be used in the function, not here. So, and what it does is that, so you don't forget, in our Inorder array we actually need to keep track of the position of each of these values, so that we can use it to build the range of the left and right subtree. So that's why I'm having the Inorder array. Also we'll be having something, the Preorder index. So this one is going to be helping us to keep track as we are moving from one index to another in the Preorder array. So fine, we are gonna be globalizing the Inorder index map, and why we are doing that is because we really want to populate it. It's empty here, so we want to populate it, and we don't want it to be limited or look out to this function alone, because we will need it in the other function we'll be creating. So and what we now do is that for I comma value in enumerate in order. So and why we are doing this is that we want to create a map, an hash map that will contain key value pair, right? So the key value pair for each value in our Inorder array, we want to put them into a map, and this is how we're gonna be doing it. So map each value to their position, so that way we can easily keep track in one time. I mean, in a constant time, you can easily get, okay, what position is value 5, what position is value this. So okay, after doing that, now we just want to return a new function, the binary tree that is gonna be this is gonna be a function binary tree. Let me just call it binary tree because we're gonna be calling this function recursively, right? It's going to help us to build a tree. So now, so this preorder and another this function is just a container, basically a container for this another function here. Okay, return binary tree of 0. Don't forget, we'll be passing in the left and the right, and this actually corresponds to the two extremes of the Inorder transversal, right? And what it means is that don't forget, we have a range. It's out of that range that we can select the left subtree and the right subtree. Don't forget, if the left subtree contain a content, if it contain a value, then we need to actually create a node for the left subtree. But when it becomes empty, then we just go on to create node for the right subtree. Once the right subtree also become empty, then that's all. So that's how we keep track of, okay, this particular element that is pointed at by the preorder index, is it going to be to the left or to the right? It depends on whether the left or right are empty or not. So, and we are going to be knowing that using this range of values. So you see that it actually covers the whole length, starting from 0, the left, and length of Inorder -1, which is the right. So we are going to be sending in the preorder array also and the Inorder array, so that we can make use of them. So okay, now let's define the function binary tree. Let's define this function now. So it's going to be taking a left, which is an integer. It's going to be taking a right, which is also an integer, right? And it's going to be taking a preorder, which is actually a list of integer, right? And it's going to be taking an Inorder. Similarly, it's going to be a list of integer. So and it's going to be returning something like a tree node, right? So now let's jump into action. Sorry, is there an error with this? The binary tree, left, right, integer, preorder, list of integer, in order, right? Here should not be like this. So okay, now if left is greater than right, return none. So you might be wondering, why do we start with this? Don't forget, like I said, we are going to be recursively calling binary tree, this function binary tree, to create the left and right subtree starting from the root node, right? And because we are trying to do that, anytime we are trying to create a particular node, but now the left subtree is now empty. Don't forget that this left is initially 0 and right is initially length of Inorder -1. They are the two extremes. So once they can get so close to each other that left now become greater than right, definitely that particular array is empty. It's just like saying an array of 0, 5. You see that that range is not empty, right? It will contain 0, 1, 2, 3, 4. But consider an array of 5, 0 is actually empty. It can't work out. So we want to return none to simplify that. Okay, at that point, don't create any node any longer to that particular subtree, whether right or left. Okay, what we want to do now, once we have the value, so don't forget that our preorder index, don't forget preorder index is what we defined right here up here, so to point at the index. So therefore, because we are going to be using it in this particular function, we are going to declare it global preorder index. So getting that value now, what we want to do is that we want to tap into our Inorder index index map to get it. You understand? To get that the position of that value. So that's going to tell us, that's what we're going to use to tell us if there's going to be, if the next node is going to be to the left or the right, depending on whether that left or right is empty. So we are going to get the position, and by getting this, don't forget to create the node. So we want to create the node, don't forget, so we are creating node out of, based on that particular value VAL. So don't forget, we are actually creating it in the same sequence as the preorder array, right? So now that we have our node created, we want to define the node.left. So let's go and create a node.left. So, and that will be us calling this new function and leaving it to the fate of, does it is the left array empty? And now we can do that is that wait, sorry, we are gonna start from left, so which is initially 0, to Inorder index -1, right? So, and then we can pass in our preorder and Inorder. So doing this now is going to be you see, Inorder index at this point will be 2, because we our root node is 5 and the position of 5 in the Inorder array is actually 2. So Inorder index -1 will become 2 minus 1, right? That will be 1. So you see, left is 0, indicating that okay, now there is now shorter, the range is now shorter. So at a point whereby left become greater than right, which is which could be Inorder index -1, at that point, then there's no need to create that new node to the left. We have to create it to the right. So that's simply what we are doing here. So Inorder is what we pass here. So similarly, we're going to create the right array now. So binary. So don't forget, at the point whereby left become greater than right, then it's just going to send in none. So instead, that's why we see that return none. Yeah, we have return none. So similarly here, we're going to be sending in Inorder index +1. So that will be the range for the right, comma the original right, GHT, and then we're gonna send in preorder, and hey, why is this thing like this? Preorder and Inorder. So this way, after doing this, we can just simply return our node. So that way, right? Because this is simply what we wanna do: create the node, assign the node left and right based on that range of value that we are defining. So, but one very crucial thing is that we have to increase our preorder index, so that it's go and reference we have to increase it by 1, so that it's going to reference the next element to be created. So don't forget, we're traversing through the preorder array. So right from 5 is going to create 9, then 2, then 3, while Inorder index is going to undo whether it's going to create it to the left or to the right. So that's simply what we're going to do. So to give this a little bit of taste, a little bit of good representation, fine, we are returning the node, but node is just gonna come as a 3-node instance of the 3-node class. So we want to give it a good representation by putting it in string format. And what we're gonna do there is that each time, don't forget that binary tree is helping us to actually navigate the preorder index. So each time like that we come across a new value, we just want to add that value and append it to our string, so that we can have a good representation. So string of value plus, let's give it this formatting, so simply like this. And then after calling this function here, at the end, you can just print strs. So let's run this function and see how it goes. So at least we'll be able to have a good string representation of the answer. Okay, we have an error. Local variable. Oh, sorry, we have to declare the string also as global, right? we have to declare, because we defined it outside, and I actually defined it outside because I don't want to be using print function inside the recursive global STRs. I don't want to be using the print function inside this function, or else it's gonna be printing each and every value. So let's see. Okay, right here we have 592347 printed, which is just exactly the Inorder element value in the Inorder array. So don't forget that we are actually using the Inorder transversal, so, and that's what we really expect. So if you print the node also, okay, this node is printed, you see that the node is also printed here, which is actually node 5, so which corresponds to the root node. You see that now we have effectively created a binary tree from Preorder and Inorder transversal. This video seems super long, and I'm so sorry for that. I really hope you understand this. Kindly do subscribe to my YouTube channel, please. Thank you. Have a nice day.